Hello, today we're going to talk about structure 3.1.8 and 3.1.9. This is an HL only topic, and it has to do with all kinds of different information about transition elements. So let's review the real basics about transition metals. There's our general periodic table. We're going to focus in on the D block, where we have our transition elements. And for the most part, for IB chemistry, we're going to really focus on the first row of the D block, which has electrons in the 3D sublevel. The biggest thing about transition metals is that they have variable oxidation states, so they can form ions of different charges, and a notable exception is zinc. So we're going to talk about why the transition metals have those variable oxidation states, and it has to do with their ionization energy. Let's start with iron as an example. That's a really common one that we talk about. So iron has the outermost electrons in the 4s and 3d. Okay, and if it's neutral, it has 4s2, 3d6 as its valence electron configuration. And I use the term valence electron kind of loosely here because the d orbital is kind of weird. So let me draw that out actually so you can see. We have 4s and then 3d. Now because it's a d sublevel, there's going to be 5 orbitals. And according to Hund's rule, we fill 1 in each before we double up. So there's our 3d6. And so because of this, iron could do a couple different things when it's forming ions. It could lose all 6 of these. That's not as stable. It could just lose this one because the electron repulsions in that single orbital are a little bit greater because it has the 2 electrons in the same, similar space. It could also lose instead the 4s sublevel. It could lose these 2 electrons instead. One thing that you need to know, and this relates to ionization energy, the 4s and 3d sublevels are very, very close in energy. So it requires a very similar amount of energy to remove electrons from either sublevel. And as such, it allows the elements to be kind of flexible in the ions that it forms, because it can lose electrons from different spaces due to the really, really similar amounts. All right. So iron is capable of producing ions that are 6+, 5+, 4+, 3+, 2+, and even 1+. But the 3+ and 2+ are the most common and the most stable. So really, anytime you see elements that have multiple oxidation states, it's because of that 4s and 3d sublevels being very close in energy. Let's look at zinc here. Zinc has the outermost electrons 4s to 3d10. So its orbital diagram looks like this. And I'm just drawing it quickly for simplicity. It has a completely full 4s and 3d sublevels. And as such, it's not really considered a transition metal, even though it's in that D block. And that's because when zinc forms ions, it's pretty much only going to lose the 2 4s electrons. And so a zinc ion would look really just 3d10 as the outermost electrons. Which is interesting. So zinc, even though it's in the D block, is not considered a transition metal. Okay, so you definitely need to be able to write electron configurations for all of the elements in the first row of the D block. And we've talked about iron and zinc already. Now, typically, it's going to work for neutral elements to fill in the 4s first, and then start adding to the 3d, however many electrons it needs. The only 2 elements that don't follow that trend are going to be chromium and copper of the elements in that first row. Chromium has 24 electrons total, 18 of which are in core electrons. So we have 6 additional electrons. So you could do 4s2, 3d4 for the additional electrons. However, what happens because the 4s and 3d are very, very close in energy, let me write this out, 4s, 3d. If I were to do it like this, right, it actually winds up being more stable for the extra electron from that 4s to go ahead and fill in the 3d. And that's because then each electron has its own empty orbital, or its own separate orbital, rather, and you have fewer of those electron-electron repulsions, so it winds up being more stable for chromium to do 4s1, 3d5. And so you definitely need to know that about chromium. Copper is very similar. Copper has 29 electrons total, 18 of which are core electrons, so that means you have 11 additional electrons. You could do 4s2, 3d9 if you followed the pattern, and that would look like this. 1, 2. Okay, that would be 3d9. Again, it's going to follow the same pattern that chromium follows, where it's effectively the d sublevel is going to steal an electron from 4s and fill that in. Because all of those orbitals in the 3d sublevel are effectively the same amount of energy, it's going to be a little bit more stable for 4s to have just one electron in that orbital and the completely full orbitals in the 3d sublevel. So really make sure you know it should be 4s1, 3d10 for copper. And so make sure you know copper and chromium as the 2 exceptions to following the pattern of filling the s and then extras in the d. So transition metals have some magnetic properties, or some of the transition metals have magnetic properties. There's 3 that are ferromagnetic, that have that permanently unpaired electron situation where they can affect a magnetic field. So these ones are going to be magnetic, right? You can also see situations where other transition metals are also able to have the unpaired electrons that reinforce an applied magnetic field. And that's because of their electrons in the outermost energy levels, so 4s and 3d. If they are unpaired, it winds up where they can align their spin, because they're all pointing the same direction effectively, or spinning in the same direction. So like iron, for example, looks like this. Right? And so that 4 of the electrons there are unpaired, right? They don't have another electron in their orbital, and they can align their spins. And if you apply a magnetic field, those unpaired electrons can reinforce that magnetic field and strengthen it effectively. So that's really interesting, and many of the transition metals are able to do that because of their unpaired electrons. For IB chemistry, you don't need to know the difference between paramagnetic and diamagnetic. You don't even really need to know ferromagnetic, but just have this idea that unpaired electrons are going to contribute to the magnetic properties, and that should be enough depth. Now, because of these metals having these variable oxidation states, it makes them very useful as heterogeneous catalysts. So that means the solid metal is going to basically provide a surface where your 2 reactants, or 3, or however many you're reacting, but basically they can bind to that solid surface, and it allows the reaction to proceed more easily and turn into a product, whatever the product is, or 2 different products, or whatever the reaction is in particular. By holding on to it on the surface, it is more likely for it to collide in the correct orientation, and that helps, improve the rate of the reaction. So there's 2 examples I want to kind of share with you. You can use iron, solid iron, to catalyze the reaction for the Haber process, which is 3 hydrogen gas and nitrogen gas, 2NH3. So the iron acts as a surface for the reactants. And another very common example is nickel. Solid nickel can act as a surface for hydrogenation reactions, where you have something like C2H4, which is an alkene reacting with hydrogen, to form C2H6. So you're breaking the double bond and filling in hydrogens on the carbons. That's hydrogenation. And so those are just 2 examples of using the solid catalysts, providing that surface there. Now, another important feature of transition metals is that they can form complex ions. These tend to be, well, transition metal solutions tend to be colorful, and we're going to talk about why they form these colorful solutions in section 10. But for right now, let's talk about how the transition metals form these complex ions. Because they have those, again, variable oxidation states, you have a variety of unpaired electrons, it can form these coordinate covalent bonds. So let me give you an example. I can have something like, let's do cobalt. Cobalt combined to water molecules. I'm going to show it like this. And I'm going to try to show you the 3D positioning of it. And I'm drawing it like this instead of saying H2O because it does attach to the lone pairs on the oxygen. And we can form 2 more in this situation. And so the dashed lines are going back behind the plane of the page and the wedges are going in front of the plane of the page. So in this case, we've got 6 water molecules being able to attach to that cobalt. And we would draw brackets and give the charge on the overall complex ion on the outside. Now, the way that you would write the actual formula for this would be cobalt H2O 6, 2 plus, like that. So there's an example of a complex ion. Now, effectively, so you've got your cobalt, which is, has a positive oxidation state. It's going to attract the lone pairs on the oxygen there to form this complex. Now, because water's neutral, it's not going to contribute to the charge one way or the other. And so that means if the charge in the overall complex ion is +2, the cobalt must have a +2 oxidation state to contribute to that overall charge. So this creates a lot of very different structures of ions with different ligands. You're going to see typically if there are 6 attachment points for the ligands, that is going to form an octahedral shape. Octahedral. If there are 4 attachment points for the ligands, it's going to be either tetrahedral or a square planar. You don't have to be able to figure out which is which for this class. And if there's only 2, then it's definitely going to be a linear. So yeah, that's why I drew this one as an octahedral shape overall to show how those 6 ligands are attaching around the central carbon. I'm sorry, central cobalt. So let's talk a little bit more about the ligands that can help form these complex ions. Ligands tend to be Lewis bases. And Lewis bases will donate electrons. Okay, that looks like bases. This is bases. This is bases. They donate electrons. So kind of like that water example that we saw in the last slide. The lone pair electrons on the oxygen were being shared to the cobalt atom. So water is definitely a good example of a ligand. Another one would be things like ammonia. And that's because ammonia has that lone pair on the nitrogen. I'll go ahead and draw water so you can see it. Those lone pairs on the oxygen. You can also have things that are charged, so things like cyanide is a good one. Cyanide looks kind of like this, and it has a negative charge overall. The electrons can be donated. And another good example would just be like a halide ion. So like chloride has those extra electrons that can, again, act as Lewis spaces. And the transition metal itself, whatever it is, like I have the cobalt from the last example, that's going to be acting as a Lewis acid, which is accepting the electron pair from the Lewis space. So all of those examples of ligands that I showed you were monodentate, meaning they bind once to the central transition metal. And so like, let me give you another example. Like if I have copper and I'm going to attach to, let's use chloride. And I'm going to draw it as square planar, but it could be tetrahedral. It doesn't really matter for this class, but let's say it's like this. And it could have a charge of -2 overall. So the formula, if I write it this way, CuCl4, 2-. Because the chlorine is only attached like once, each chlorine is attached once to that central copper atom, we call the chlorides a monodentate ligand. You should also be able to determine the oxidation state on the copper. So like a chloride has a -1 charge, and there's 4 of them. So that's -4 overall. The copper must be +2 in order to get the overall charge on the compound to be -2. Make that a little clearer. Now, the number of lone pairs attached to that central transition element is called the coordination number. Coordination number. So in this case, the CuCl4 complex ion has a coordination of 4 because it is attached by 4 lone pairs to the central copper. Let me give you one more example with some monodentate ligands. Let's do, and I'll just write the formulas. If I have CuH2O6, and let's say it's 2+. Remember that water is neutral, so it doesn't matter how many waters are attached. Whatever the charge is on the complex will be the charge on the transition metal, +2, or oxidation state on the transition metal. And in this case, because there are 6 waters attached, we know that the coordination number for this one is 6. So those are how monodentate ligands work. You can also have polydentate ligands, and I included this image down here. This is ethylene diamine, and this is a single molecule, right? So it would be H2N, CH2, CH2, and H2. And so that has 2 lone pairs on the nitrogens that can both coordinate with that central cobalt atom. And so we call that a bidentate ligand because it has 2 spots that are coordinating with the transition metal. But still, this would have a coordination number of 6 because it is attaching with 6 lone pairs. You can also have like tridentate ligands or hexadentate ligands. Really common hexadentate ligand is EDTA4-, where it will attach in all 6 positions, and it will have a coordination number of 6. So let's look at a few examples for this section, or these 2 sections. Draw the orbital diagram for the CO+3 ion. It did not specify, so I'm going to go ahead and draw everything. Weird looking box. All right, so 2s, 2p, 3s, 3p, and those are completely full. Second energy level, third energy level, and then the outermost. So cobalt typically has 27 electrons. So it would be 4s2, and then we would fill in the 3d with the additional 5 electrons. 1, 2, 3, 4. I'm sorry, 7 electrons. So 3d7, 4s2. But that would be for neutral cobalt. When you're forming an ion of these transition metals, very often they're going to lose their 4s electrons first and then lose electrons from the 3d. So in this case, for cobalt 3+, we will lose those 2 electrons in the 4s orbital, and the third electron lost would be this double up there. Oops, I'm sorry. This one, double up. So this would be 3d6. So your overall electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So again, with transition metals, typically you're going to see the 4s electrons leave first, and then you'll start removing from the 3d. Now for this one, very similar orbital diagram for the Cu+ ion. I'm not going to draw all of the core electrons, but you probably should because it did not specify for just the valence electrons. But to show this a little faster, I'm just going to show the outermost. Now remember that copper is one of our exceptions. So neutral copper has 4s1 and 3d10. So like this. And then it's forming a +1 ion. And it's going to follow the same pattern that the other transition metals do, and even though its neutral electron configuration does not follow the pattern. It's still going to lose electrons from the 4s orbital first, so it's going to lose that 1 electron to form a +1 ion, and so it would just be 3d10. So its overall electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. And that's it. Now here's an example of a justification question or an explanation question that could be applied to these sections. Explain why iron can form 2 stable cations, while magnesium forms only 1. A simple explanation could involve that iron is a transition metal, and it has outermost electrons in both the 4s and 3d. So, and because those electrons are because those sublevels are very, very close in energy, it could lose electrons from either place with a similar amount of ionization energy. Magnesium, on the other hand, its outermost valence shell is 3s2, like that. It does not have any d sublevel electrons at all. There's no such thing as 2d. So magnesium can really only form a +2 ion because it's going to lose those 2 electrons in its outermost orbital. And then let's go ahead and link this back to structure 2.3, arguments for and against including scandium as a transition metal. Scandium, if I'm just looking at the outermost electrons, is 4s2, 3d1. It only has 3 electrons past at their core noble gas configuration. So scandium is a member of the D block. It has electrons in 4s and 3d and as a neutral atom. So that could be an argument for including it as a transition metal. It also has an unpaired electron in the 3d sublevel as a neutral element. All good arguments for including it. In theory, it can form multiple oxidation states. It could lose its 3d, it could lose only its 4s, it could lose all 3. However, it only really forms one stable cation, and that stable cation is Sc3+, where it's going to lose all 3 of those outermost electrons. So because it only has one stable cation, that would be an argument against including it as a transition metal. Kind of like zinc, which only forms one stable ion and is not considered a transition metal. So you could argue either way for that one.